Hello, I'm Stacy Ross, and this is my presentation for Lab 4, Circuits and Capacitors. The purpose of this lab is to use the principles of energy conservation and current conservation in order to predict the behavior of circuits containing resistors in series and parallel, as well as use multimeters to measure conventional current and potential differences, and examine the behaviors of ohmic resistors and capacitors. The loop rule states that the sum of potential differences in a loop is zero. The conservation of charge states that the charge flowing in is equal to the charge flowing out. The steady-state definition is that the variables which define the behavior of the system are not dependent on time. Ohm's law states that voltage is equal to current times resistance. Capacitance is equal to charge over voltage. To begin this experiment, I recreated the series circuit in the given diagram in CCK. We are asked to predict the readings of the two ammeters. Using Ohm's law, I calculated that the current would be equal to voltage divided by resistance. Ohm's law indicates that the ammeter would read 0.0204 amps. Upon recreating the circuit, I confirmed my prediction. However, the ammeter was slightly less precise than the predicted value. Both ammeters read 0.02 amps. Next, we're asked what happens if we reverse the direction of one of the ammeters. If the ammeter is reversed, the reading would become negative 0.02 because the flow of the current would be reversed. Next, I replaced one of the ammeters with a voltmeter. The voltmeter read 3 volts, while the remaining ammeter showed 0 amps. The 3 volts are expected from the two 1.5 volt batteries. The current becomes 0 at the ammeter because the voltmeter has infinite resistance and does not allow any current to travel through it. Essentially, the circuit becomes open. Next, I removed the voltmeter and closed the circuit with a wire. I measured the potential difference at various points using the voltmeter. I recorded the following potential differences, and the sum of the potential differences was 0, as predicted by the loop rule. Next, I was asked to create a graph of potential versus position of the circuit starting from the partial graph that was provided. The electric field is the negative gradient of the potential, so where the potential difference was large, the slope of the graph was steep. Using the data collected, I produced this graph. Throughout the readings, the ammeter remains constant at 0.02 amps because the circuit is a closed loop and current travels through the wires rather than being stopped by the resistance of the voltmeter. Next, I observed the potential difference between both ends of the 100 ohm resistor again, which was negative 2.04. After noting the reading, I replaced the voltmeter with an ammeter in parallel with a 100 ohm resistor. The current in both ammeters became 0.06 amps. Due to the added ammeter, less current passes through the resistor. A decrease in resistance results in an increase in current, as predicted by Ohm's law. Using the recorded potential differences in currents, I calculated the expected resistance of various elements. The calculated resistance was slightly higher than the actual resistance. This can be attributed to the lack of precision provided by the ammeter. In the second part of the experiment, I explored RC circuits. To begin, I connected a 9-volt battery, 20 ohm light bulb, and a 200 millifarad capacitor in series. I observed that the light is initially bright, however it dims and turns off as the capacitor charges. Next, I removed the battery and connected the capacitor directly to the light bulb. The light again lit up initially but faded away as the capacitor discharged. When the capacitor is charging, current flows through the circuit, causing the light bulb to work. Over time, however, the charge collects on the capacitor and the current becomes 0, making the light bulb fade away. When the battery is removed and the capacitor is discharging, the current flows through the circuit initially, causing the light bulb to work. However, over time, the capacitor loses its charge and the current returns to 0, making the light fade away. I recorded the time it took for the capacitor to discharge using a 10 ohm light bulb, then repeated with a 20 ohm bulb. The times were 10.2 seconds and 19.5 seconds respectively. The lab explains how to compute the time constant of the circuit. The time constant is the time at which the voltage difference has dropped to 1 over E of its original value. If we consider a circuit containing only a charged capacitor and a resistor, the conservation of energy equation reads that the sum of the charge and voltage of the capacitor and the resistor is 0. Because the change in V is equal to Q over C, we can write this as Q over C minus I times R equals 0. I is equal to the change of charge flowing over the capacitor with respect to time, so we can rewrite this equation as Q over RC plus dQ over dt equals 0. By solving the differential equation, we get that the change in V is equal to the change in V naught times e to the negative t over RC. Taking the natural log of both sides, we get the equation shown above. A plot of the natural log of the change in V over V naught versus t should yield a straight line with a slope of negative 1 over RC. RC is called the time constant of the circuit. Finally, I created a series circuit of a 9-volt battery, 200 millifarad capacitor, and a 30 ohm light bulb. Once the capacitor was charged, I recorded the voltage across the capacitor and found it to be 9 volts. I then removed the battery and allowed the capacitor to discharge. Using the timer, I stopped and started the simulation to collect data on the voltage across the capacitor for 20 seconds as it discharged. My data produced the following graph. The voltage decreases exponentially with time. The graph produces the equation shown above. Using the relation between slope and the time constant, I found the time constant to be 5.988 seconds. Now for the reflection questions. We're asked, what if I were to do this lab in real life and use an actual emitter instead of the ideal simulated emitter? What effects would it have on the circuits I hooked it up to? In real life, emitters do have some resistance. The readings would be slightly lower than the idealized one in this lab. Finally, what if I had used a real battery to charge a real capacitor with no resistor in the circuit? How long would the ideal model predict the capacitor would take to charge fully? Would this prediction happen in real life? In the ideal model, the capacitor would be charged instantaneously because there would be no resistance. However, in real life, all components have resistance and it would take some time for the capacitor to reach full charge. That's all. Thanks for watching.